Okay, so we are officially recording class right now. And so it's Wednesday, October the 25th. And I'll just kind of start talking. We're actually going to kind of revisit a slightly different uh, data model called the raster data model. So today you're actually going to be creating raster data from vector data. We're going to talk about a couple of different methods in which we can do this because we're going to be doing things called interpolation and extrapolation. They're big fancy words for just filling in numbers that we don't know using known values, right? We do this all the time, right? If your rent is $1,000 a month and you move in halfway through the month, basically, how much do you have to pay? You got one person in class today. How much do you have to pay? Yes, $500. We prorate it basically, essentially prorate it. And so in this case, what we're going to be doing is looking at issues of place and space. This is just a simple ratio here, but now we take into account place and space for all these things here. I got a couple of examples right here. This is like a rainfall map. This is a temperature map that you might see, like current temperatures in the United States. And we look at this thing here, and these are kind of what we call isotherms. And we kind of fill in these things right there. So these lines right here are, in theory, lines of the same temperature. And then we fill in these nice, pretty colors. And so that red is warm, blue is cold, and it looks nice and pretty here. But one of the things about this is, do we know all the temperatures everywhere in the United States? How do we know what it is right here, right here, right here, where they're not filled in? I don't know. Yeah, the same colors. Also, we've got temperature monitoring stations. So if you've taken my class or we've gone to the Climate Prediction Center, and I forget if we've done that in this class, but we can go to the Climate Prediction Center and download some data. And I'm pretty sure they're available in external links. So we can look at the max temperature, min temperature, snowfall, snow on the ground for particular days. And it might give us about 115, 120 weather stations in North Carolina, about a few thousand across the United States. Even then, there's still wide ranges of areas where we don't know the temperature. So how do you know what the temperature is at that area? You can guess? How do you know? We're gonna kind of talk about that today. Okay, we'll kind of figure those out. And we see these maps all the time. You turn on the news, you're going to see a map like this. Another thing, this is computational science and engineering, and this is, I think, snow rainfall. And so I think it's gallery of states, 30-year averages of average annual conditions over the most 3 recent decades. And I'm pretty sure this is rainfall across the United States. Does it know where the rain falls in every single place in the United States? No. But we know where it falls in a number of other places. So if the temperature is 75 degrees, and like Caitlin said, I asked her about the temperature today, it's 75 degrees out in Asheville. We look at Hendersonville, which is kind of right down the road there. Or we look at Rutherfordton or Morganton. What do you think the temperature is? Is it close to 75 or really far from 75? This is going to be close. Why? Because it's right near it. Just like the idea of if you have pay $1,000 a month in rent and you came in the second of the month, you're probably paying pretty close to full rent. And so now we take into both place and space that account for these. So to me, this is some really neat data that we're looking at here. Today, I'll mention here, or I'll revisit this. So today we're going to talk about Chapter 11, which is spatial interpolation, a big fancy word for just filling in unknown values with known values. Now, I think there's a lot of work that can be done in spatial interpolation, spatial extrapolation. We're going to look at the exercise 8. We're going to work on exercise 8 today, where I had a student, it's probably been about 8 or 9 years, where he did some research to look at the different interpolation extrapolation methods to figure out what one has the highest range of values. Because, if the temperature is 75 right there, what's the temperature here? Could be 74, could be 73, it depends. And so there's different methods called Kriging. We have something called IDW, inverse distance weight. Does that ring a bell? Inverse distance weight? Where have I used that term before? Inverse distance weighting. Exactly. Oh, we got someone who's been paid. So we're clustering exactly. What's the definition of a neighbor? And we use something called IDW squared. We'll talk a little bit more about that, but what's the definition of a neighbor? Things that are closer to you have more weight than things that are further apart. And so you get this zone of indifference that you can also talk about. Hey, after 20 miles, it's not going to have any type of impact. And so is the air temperature in Elizabeth City going to have anything to do with the air temperature in Asheville? Probably not. So we would look at all the stations around Asheville to get a good idea as to what the temperature in Asheville is if we don't have the temperature for it. And so as you can imagine, all we're doing is kind of a weighted average. Remember that weighted average stuff that we did a long time ago? But we're doing the same exact thing here. So interpolation, then we'll talk about density. Because density, we're going to be looking at a map of deer vehicle collisions for like 2011 across the entire state. And it's really ugly. So how do we turn it into something that we can make sense out of? And we did the same thing with like cancer deaths, but we remember we need to normalize by population or group those into applicable units, where something like deer vehicle collisions is more, we don't rely on population for those. And so we can break those down into quadrants or cells in this case. Next week is the first. And so I'll go through chapter 12. Last year and in previous years, chapter 12 was kind of an add-on here where we talked about some things, but I'll talk a little bit about chapter 12, which is geographically weighted regression. So we talked last week about regression. What are all the factors, the y equals mx plus b stuff, but with geographically weighted regression, one of those b's is also an identifier for geographic location. So it takes into account, it creates a y equals mx plus b that also has location attached to those. And then we'll talk about addressing ancillary issues in geostatistics. So we'll talk about things like heteroscedasticity. We'll talk about things like multicollinearity, all those other things that we haven't talked too much about, but someone will be sitting in the back of the room saying, have you thought about this? Have you thought about that? Have you thought about the other thing? And then we will kind of prepare for the final exam. Once again, the final exam, open note, open book, open resource. I think everyone who takes it does well. You know what I mean? Do well, make sure you know what you're doing. There's a nice hands-on component for all of these things here. And so one of the trademarks of my class is, concepts and all that other stuff are immaterial if you can't apply it, using the software, using the skills. And, I'm pretty amazed at just the jumps that people have made from looking at a bunch of cancer deaths almost 3 months ago to now, where we're making maps. We're doing a lot of really neat things that'll proliferate your research here and beyond. And then in 2 weeks, we're going to have the final exam given during class, because in 3 weeks from yesterday, I will be out in San Jose, California, out at NASA conference. And so we're going to meet other people who have received NASA funding. Hopefully in the future for this conference, we can take out some students, but I didn't really know what to expect. So I was kind of like, all right, let me go myself, get the lay of the land and things like that. And I think I've sent out to the department, actually going on that week, there was a virtual NASA conference going on related to data science. And so has anyone seen any of that recently? Miss Lambert sent it out probably about 3 weeks ago, but if I think of it, I'll post it, the announcement. So it's related to data science. It's put on by NASA. You can attend in person, but it's on a military base. So if you are an international student, it's really hard to get on, if not impossible. And even if you're a national student, it's really hard to get on as well. So, going through all these gates and things like that. And then for any students taking this class as an undergraduate who's signed up for 4130, your semester will be over unless you have some outstanding work that needs to be turned in. So between the 8th and the 28th, that almost 3-week period, you can work on your position paper, any outstanding projects that you need to do, or if you're taking this class as an undergraduate student and you're signed up for 4130 and you want to do the position paper now and you want to do the extra readings now, you can do that, because right now there's a couple of students registered for this class who took this class as 4130 a while ago, and they're like, well, I just signed up for 5130. When do I get my A? And I'm like, 4130, 5130, a little different. You got to do the position paper for it in addition to the extra reading. So I unfortunately have gotten a little bit of pushback from them, and not from them, but I've kind of gotten a little bit of pushback from them about, they're two separate classes of these. So if you do want to take this or get credit for this as a graduate student, or if you're like Benjamin and you're taking this as a grad class as part of our ADM program, you need to do the position paper where we go prove or disprove something. You can use some of the data that we've worked with. You can go create your own data. But we have some hypotheses out there. We did a whole thing on clustering, so we can talk about areas of high crime are clustered in low income areas or something like that. And we can look at how much the crime and the income overlap with each other. Count the number of hot spots. We did an exercise a couple of weeks ago where you went and counted the number of hot spots for a particular area. If there's no overlap between those, there's ways that we can explain those, where we apply the techniques, or you could just make a statement where I said, COVID is higher in urban areas, okay, versus rural areas, or versus suburban areas, or suburban areas had the lowest rates of COVID compared to rural and urban areas. What's the definition of suburban? Between 10 and 20 miles from a city. So those are going to be the things that you're going to use in a GIS to kind of figure out and extract. And so a couple of weeks ago when we were talking to James and working on those two-tailed t-tests, and he said 15 miles from a city, well, just back it up with 15 miles or 10 to 15 or whatever. And so I look forward to those position papers. I'm pretty sure under modules right here. And those of you who are kind of taking this class as an undergrad right now, like, hey, I just want to go do this and knock this out, because I do have a couple of students who are registered for the class. They did the position paper as an undergraduate and said, I'm going to knock this thing out now, and they're going to get whatever they earned in my undergraduate class. But you can see a couple of position papers that were done here. I really kind of like these. I've got a template for this, but this was COVID spatial analysis of COVID-19 variation between urban and rural counties. This is pretty straightforward. It's got, you can see the mean. We've got some descriptive statistics. We've got some two-tailed t-tests, all this other good stuff. And we've got some nice, pretty maps right here. So you know me, I love looking at maps. People love looking at maps too, even though we take a lot of effort to kind of go through and make those. This was a really good one as well. And there's a poster for this on the other side of the room, where that V, who's one of our graduate students, she wanted to look to see if there was a difference in suicide death rates between pre-COVID and COVID. And so she went and downloaded the data. I'm pretty sure she had a nice little calculation where we calculated suicide rates. And so we calculated suicide rates for 100 counties at the county level for 2019. For 2020, and all we did was just a nice two-tailed t-test where sample sizes were equal to 100 for these rates versus these rates to see if there was a statistical difference in suicide rates, if they had gone up or gone down. These maps don't do too much to me. I probably would have, we can see change here. Okay, we can see change where it goes down and goes up. I don't like this legend right here where I said stays the same, goes down or goes up. That might be a better descriptive statistic, but look at this thing here. Does this ring a bell? What kind of results do we get? The suicide rates actually went up, just not up enough for them to be statistically significant. Close. We're at 0.1699, close. They did go up, but not enough for statistical significance. There's no P equals 0.83, we're at 0.9, 0.95, 0.99, or 0.0, where the p-values get inordinately low. Okay, and so what are some things we could do to circumvent if we really, really wanted to? Maybe we could group these at the zip code level, maybe. That might be a little bit difficult because you might run into some small number problems, but you're going to have a higher sample size. And so there's ways that I don't want to say we can circumvent these, but remember, we have small sample sizes. We're going to run into larger margins of error. So if we had these differences in these rates at the zip code level, this number, this p-value is going to be a good bit lower because our sample size is a lot higher and our margin of error is a lot smaller. But we might get different results if we're grouping this at the zip code scale, because we got 763 zip codes. And so if we have a real low population zip code that has 1 or 2 suicides, what's that going to do to the rate? Move them inordinately up. Or we've got, value, got a lot of zero population, well, you're probably going to have 0 suicides. And so next week, we'll maybe talk about some of the ways to kind of circumvent those. And we did talk about some of the ways we can circumvent that when we did change detection analysis. And remember when we did that change detection analysis, we said, hey, instead of looking at just 1 year to the next year, hey, let's look at 2010 to 2013 versus 2014 to 2017, and then group these into these 4-year periods so we get larger numbers. So instead of going from 1 to 3, where we have a 200% increase, we might go from 13 to 15, where we have a 17% increase, or whatever that math, whatever the math is there. And so, those are some suggestions that you're going to run into, because seeing things like 200% increase are really telling, but we run into those when we go to like from 1 to 3 or 2 to 5 or something like that, when in reality, if we were to go from 100 suicides to 200 suicides there, or 100 deaths to a 200 deaths, we know we have a public health emergency on our hands. And so I will talk about those a little bit next week. But under the announcements, we talk about that. Today, in preparation, we've got 2 more classes. Like I said before, I've been clicking on this data set today. This is Air Now because I really wanted to highlight this. Has anyone in any other classes gone to like the EPA data download site and gotten these? I'm looking for the one person in class to kind of nod their head. No, I think so. And so if you're taking sustainability or environmental science or any of these other things, you can go and download data for things like PM, particulate matter, ozone, from the Air Now for recent days that are not available in AQS. Now I might have to look at this at the break right here, but I could go download these and I'll have like a list of them like over the last year. I have the latitude, the longitude, so we can run some simple tabular calculations to kind of put them into individual lats and longs and then group these by average over the last month or something like that. And so, as you can imagine, when we start looking at space and time all together in one, it gets really ugly really quickly. And so our GIS software has some powerful tools to look at space and time, but they got to be in the right columns. And that kind of gets a little out of my, I don't want to say out of my skills, but I just really haven't been keeping up with the spatiotemporal tools as much as I should have. But we could download PM for North Carolina, and it will just give us a big CSV file of everything that's in there. And so if I think of it, I'll kind of look at, I'll kind of look at that as well. So one of the other things that we are going to talk about here, and so what I'm going to get into is we're going to start looking at the idea of raster data. Now, this is a great example of raster data. You can see that I've connected to a server, and so I've got a secure server here on services. So I can go and add items, I can add folders, I can add servers right here. So if I go to add server, if I know the information about it, I can add a brand new server that's sitting over on someone else's database that I don't have to take care of. And so this is the North Carolina One Map. If you go to www.nc1map.gov, you can download a lot of this information, or you can connect to their server. And it's got like the latest and greatest imagery at like 1 foot resolution. And so if I wanted to, I can click on imagery. And like this is literally the latest imagery that we've got from the server. Watch this. I swear I know what I'm doing here. Okay, because most of you are taking this for the first time or taking this back in 4010. I really don't do too much I really don't do too much on raster data because I think there's a lot of synergies with remote sensing, and I think you cover this in remote sensing. But here we're looking at a image server of NCCU campus right here. So this is kind of taken of NCCU campus. And so you have to go to Google Map or Google Earth or any of that other stuff. This is probably the same data source. We have these NC1 map. It's flown by the NCGICC, which is the North Carolina Geographic Information Coordinating Council. These are the people who run GIS in the state of North Carolina. These are the people that go and set up the North Carolina GIS conference. And I know Alondra went there last year, and we kind of, not we, but you all kind of hung out for the night in Winston-Salem, and where you meet and greet all the big wigs in GIS. And the one thing about North Carolina is got a really strong and robust GIS community. And they're really good people, and they're really supportive of our universities, especially NCCU. You know, they've been especially supportive of us and providing opportunities. But every few years, they go and fly this imagery in an airplane, you know, through their photogrammetry unit. We have 2 graduates from this program that work actually over in that office on the far side of Raleigh that work in photogrammetry. Photogrammetry is making measurements using imagery, you know, satellite, drone, airplane. And so at one point in time, these were flown using airplanes, which is pretty neat. And so we can kind of zoom in, zoom out. If you zoom in enough, you can see it's made out of tiny little squares. And we'll look at some of the other imagery that we have here. You notice here I zoom out and it's not adding instantaneously. Why is it taking a little time to add? And those of you online here, you can answer too here. I don't want to put Alondra on the spot too much. Does anyone have their hand raised? No?
Could you repeat the question?
Oh, okay. Why does it take a little bit of time for this imagery to get added here? You see this imagery right here? Why does it take time for it to get added? It's not just being instantly added.
Is it, this is the source of this is a base map source?
Yeah, it's a base
Or is
map
this-
source. And where's it
So
sitting?
it's having to download it. It's on the cloud.
It's downloaded. It's sitting on a cloud, or it's sitting on that server over in Raleigh. And when we talk about the actual number of pixels in these things, you're going to be absolutely amazed by some of the math that we're looking at right here. Okay, good. Thank you, Benjamin. I go to meetings with adults, and the adults like, I want all you other adults to have your camera on. So, you know, I'm not going to make you all do that, but there's some people get real emotional about that. But if I were to right mouse click and look at properties, we can look at the properties of this right here. And if I go down to source, raster information, this has got the number of columns and rows. And if any of you have really taken a deep dive into some of the properties with your vector data, you can look at the properties, coordinate system, all that other good stuff, source information. And when you look at it for vector data versus raster data, they're going to be slightly different. But what I'm looking at right here is the number of columns and rows. So 5,310,001 and then 2,500,000 rows. And so that's the total number of pixels in this image. What is 5 million times 2 million equal to? That's a big number, right? 5 million times 2 million. 1E13. It's like 10 billion. Yes? 10 billion. 10 trillion. 10 trillion pixels. What's a trillion? 10 to the 12th? Yes. So that's 10 trillion pixels that we're looking at. The tiny little squares which make that up. And as you can imagine, when we're working with cancer deaths, how many cancer deaths do you remember us working with for a particular year? 100,000. And so we're orders of magnitude more than these. And so to render these and all these other things here. Cell size is 0.5 times 0.5. And if we were to go down a little bit right here, I would see spatial reference. And this tells me this is 0.5 times 0.5. 0.5 times 0.5. This is feet. spatial statistics, spatial reference, extent, statistics. But this is in feet. And then the uncompressed size is 29.7 TB. What's a TB? Is it terabytes? How big is a terabyte? Is that a lot? Is that a little? What are we looking at? This is big. Terabyte is like my external hard drive. And so just to store the imagery for the entire state, it's like me carrying around 29 of the, of my little 1 gig hard drives, just carrying them. So we got a lot of space going on here, a whole lot of space here. And this is stored at 6-inch resolution, 6-inch resolution. So it's really, really, really small. Okay, really small. And so we zoom out. So this is just an example of some raster imagery. Okay, I zoom out right there, and like Benjamin alluded to, it's going to take a little bit of time for this stuff to kind of pop up. Now, more traditionally, okay, because we're going to be creating these here, but from North Carolina, one map, I've got elevation. And so this is elevation right here. And I can kind of zoom into these particular areas right here. And if you start to notice here, they're made out of these kind of tiny little squares right here. But if I zoom out, the way that I colored them in is I think I set up a little bit of transparency for them here. But this is the imagery right here. This is elevation imagery. And so I kind of colored it in. There it is. And if I look at the properties of this, I look at the source imagery, the raster imagery, and you can see it's about 1 terabyte and it's stored with about 3-foot imagery. So 3 feet by 3 feet. And so here we only have about 850,000 times 328,000. And so we're working with a lot less pixels, but there's still a whole lot of them. And then the size of these is going to be about 1 terabyte because we're not storing as much spectral information, which means if I click on this, it's just going to have the elevation. That's it. Nothing more, nothing less. When you click on a picture, it's got a red, it's got a green, it's got a blue. Has anyone heard that term RGB before? When we make colors, it's just a combination of red, green, blue. So white is all colors, and then black is 0, 0, 0, which is going to be the absent of colors when we look at something up there according to its RGB classification. So we've got these here. And so I can zoom in, zoom out. As like I alluded to before, this is sitting on a server here. It's going to show up a little bit easier. But what we're going to do today is we're going to create these raster maps, just like we did weather maps or everything else, based on interpolation techniques or extrapolation techniques. And so what we're looking at, first thing we're looking at is I've got data called PM sites. This is data that I've extracted from the previous incarnation of that AirNow data. And so if we were to right mouse click on these things here, what we're looking at is we've got about 35 different stations, and this is the average PM value. What's PM stand for? Anyone joining us here? What's PM stand for? I know Tamar knows what that means. I'm staring right into the camera.
Particulate matter?
Yes, yes. Okay, what is particulate matter?
Isn't it made up of like plastics?
What's that? What's that? Plastics, kinda. Benjamin, what were you gonna say?
Particulate matter is it can be any particle in the air. There's a certain, depending on the different sensors can pick up different size particles, and particles can be anything from physical like plastic, like microplastics and stuff, but more commonly it's like carbon and chemicals in the air. Like there's certain size. I'm not entirely familiar with exactly how it works, but there's like certain size. It looks at the sizes. Basically, it takes a really fine photo, and it's able to point out all the dark spots in the photo and count all the points, and then it's able to get like a particulate matter. And based off like the size, how you measure it, it's different.
Whatever he
That,
said, yeah, that's good. But
am I
to me,
close enough?
yes, it's just junk in the atmosphere that you breathe in. The big stuff kind of gets caught in your nose. The small stuff you breathe in kind of gets into your lungs and cause long-term health impacts. They could come from anything. Volcanoes that occur in Indonesia, junk in the atmosphere, car exhaust, farming, everything, drought or whatever. So it's both natural and anthropogenic processes that do this. And if you look at the attributes here, I've got my latitude, my longitude, and the average measure value, and then I've got kind of the county that it's located in. So when it becomes available, that AQS website that I provided here or mentioned, and the site that I've mentioned in the homework will have information that you can create data that looks like this. Now you can see these stations all throughout the state here, and so what we're going to do here is fill in the missing values. That's what we're going to do. We're going to fill in these missing values based on interpolation routines and based on the existing values. Now, the other quandary that we run into is now we've got this thing here. This is a map here of deer vehicle collisions. Okay? Map of deer vehicle collisions throughout the entire state of North Carolina. We had a student, and maybe I'll look him up here, but he works as an estimator. And so he used his GIS skills to go and be an estimator to figure out how much construction jobs are going to cost. But he was one of my first master students when I started here, and he came to us from as an ecology major over at NC State. But he wanted to do a project on deer vehicle collisions, and we've kind of stuck with it. But this is a map of deer vehicle collisions. What does this look like to any of you? Any of you joining us online? What's it look like? What's it look like to you, Ariel?
Like you're just saying, like based off what I see,
Yeah.
it looks like there's a lot of them, and they're mostly like in the middle.
Exactly. There's a lot of them, and most of them are in the middle. And that's what I was expecting her to say. So what we want to do is we want to turn this into like some hotspot map or density map or whatever. So we're going to turn this into a surface. So even though we're going to be creating surfaces, the way in which we do those are entirely different. So I'm going to start kind of talking a little bit here about spatial interpolation, density. We'll kind of start with the homework, and then we'll kind of finish up with that. But density, map density or interpolation and density are two different things. Now, the thing that I'm going to start with right here is we're taking data from the Climate Prediction Center, and we can see maximum temperatures around Asheville. So we can see this red dot here is Asheville, and then as you kind of go out 40 to Black Mountain and Marion and kind of going east, and then you kind of go out west here to western North Carolina. Any ideas? What do you think the temperature in Asheville at this red point's going to be? Any ideas?
It's going to be close to it's going to be in the 80s.
In the 80s, why?
Because so Asheville sits in a bowl, so it's kind of sits at a lower. You can because of everything near it, you can make assumptions. But
Exactly. So
if it's warmer in south of it, it's higher in elevation south of Asheville than it is in Asheville. So if it's warmer there, you can assume that it's the same temperature there.
Okay, and we've got a special guest here. This is Thomas. He stopped by to say hi. Thomas came to us. He was an undergrad here, like when I started here in 2010. You graduated. What's that? You were one of my first classes, man. That was a tough learning curve. And he had worked for Duke Hospital for a while, doing like inpatient patient processing or something like that.
Yeah.
Patient processing, and he came back and got his master's and finished up like 2 years ago, right?
Yeah.
2 years ago, and you're working for the EPA now, is that right?
Yeah.
He's working for the EPA. How is it? Do you like it?
So it's a nice learning curve in that.
Okay.
There's a lot of using HICRAS and HIC-HMS for hydrology modeling.
Oh, I don't know that stuff.
Yeah.
So he's doing hydrology modeling, and you work in local, right?
Yeah.
Okay, cool.
Yeah, I was coming down the road. I said, let's stop by.
Okay. Yeah, these days we're going all remote, and I'm recording everything. So we got like 4 different sections. We've got an undergrad here. We've got a bunch of grad students here. We even got some PhD students here. So we started a PhD program in data science, and so they're joining us virtually here, and they're learning GIS for the first time. I think they're starting to like it, and so. But Thomas is one of our grads, and he was working full time, did the program, knocked it out, and I'm the bigger and better things here.
Yes.
So I'll be done in a little bit if you're going to stick around here.
Yeah.
But I'll be done in a little bit, and I think everyone else is gone here. So we're doing our talk on spatial interpolation and extrapolation and density. So we're going to do our talk, and then we'll have a break here. But we have different ways to represent surfaces. So like I mentioned before, we've got these grids right here, and essentially these grids are created from this lattice of points right here. This lattice of points, way back in the day, like late 1990s, they had these things called ASCII grids, where basically the middle of the point here could be converted to these grids right here that I showed you. Now, those grids with 6-inch resolution, 6-inch resolution for the entire state, we're talking about literally like trillions of these things across the entire state that are used to store a red, a green, and a blue. And then with the imagery, we're looking at about 3 feet, or for the elevation, about 3 feet by 3 feet for the entire state. So now we're looking at like tens of millions of these for the entire state, where we're only storing an elevation, one value. Now, all the things with red, greens, blues, we're storing those as numbers or integers, or what we call shorts, that go from 0 to 255. So remember all your bits and your bytes and all those other things. Where that we're going to be storing elevation as our floats, because a lot of times those will be extracted from what we call LIDAR. Who's heard the term LIDAR before? You guys use LIDAR stuff, Phil? A little bit. Light detection ranging as opposed to radio. And so we can just collect, high quality imagery right here. But when we talk about interpolation and density explained, we're both going to be generating surfaces. But with density, we show where the points or line and features are concentrated, because like Ariel said before, I just see a bunch of points, and there's more points in the middle than the rest. And that's what it should say. And so less points, we have a larger search radius. So we can create a search radius. Now in math class, what's a radius? What's a radius? I'm getting
Half the diameter.
What's that? Half the diameter, exactly. And so basically what we're doing here is we're at a particular cell. We want to figure out what the cell is, and we set a radius of 5 miles. It's just going to go and look for everything within 5 miles, count the number, and then do the normalize it. So it's not going to give you the actual number. It's going to give you the number per unit area. And then it's going to go over to the next cell and do that again. Go to the next cell and do that again, and do it a few million times in a couple of seconds, and calculate it for us. And so that's what this does. But where interpolation, it calculates or estimates missing values based on known values. And so as you can guess, we're going to try to estimate what those missing values are for PM throughout the entire state. Now, we can apply weights to density and search radiuses and all those other things. So remember my deer mapping or my bear sightings I did? I knew that the average area of a bear habitat was about 3 miles. They don't go too far. So it was about 3 miles. So I set the radius equal to 1. What's the area of a circle if the radius is equal to 1? Okay, and we're talking math, geometry. So what's the radius? What's the area of a circle? What's that formula? Area equals. I'm looking. How about one of you folks here? What's the radius? What's the area of a circle? Area of a circle.
Pi r squared.
Pi r squared. Okay. Pi r squared. So pi r squared, area equals pi times 1 squared, which is 1. So pi times 1. What's this pi thing? 3.14. Oh, I said the area. So the average bear habitat was about 3 square miles. So I just threw it into be 1, and so it's equal to about 3.14. What's so special about pi? What is pi? What is pi? Anyone know? It's the ratio of any circumference to the diameter for any circle in existence. So any circle in existence you can think of, really small, really big. But if we were to divide the circumference, the distance around that circle, divided by the diameter, it's equal to this special number called pi. All the time. Okay? All the time. And so it's one of these kind of constants that you need to kind of remember in math there. And it was appropriate because I could just throw in that 1 r squared. I got my bare habitat size. So essentially, when I created the bare surface, it was just look for all the bare sightings within a mile. Look for all the bare sightings within a mile. Look for all the bare sightings in a mile, and we create a surface. So with a density map, what we do is we create a density map for heart disease incidence. This might have been something we did way back in the day. Well, I'll show a couple maps. But we create a search radius around a particular area to look for patterns. And basically, we count the number of points within the distance and calculate a density. To me, the density doesn't really matter because it could be per square miles, per square kilometers, per square squares, or whatever. And so we can set some parameters right here. So I can create something like this. And so these might be heart disease death rates. And then I can do input parameters and set a cell size and set up a neighborhood. What's the definition of a neighborhood? We talked about this in clustering. So I can set up circular neighborhoods, square neighborhoods. I can set up something called an annulus, which is basically like a donut. Why are donuts important? Or especially in crime analysis, we'd set up the idea of a donut. It's called an annulus, A-N-U-L-U-S. Why do they use annuluses in crime analysis? What's so important about a donut? Right, you're going to rob someone. You're going to rob your neighbor? No. You're going to go down the street, but you're not going to go too far away that you're not familiar with it, right? So they have this whole idea of like donuts when you commit crimes, because you're not going to go rob the person 2 doors down. You might go half a mile down, but you're not going to go more than a mile and a half away because you're not familiar with that neighborhood, so you can go home. And so the idea of using these annuluses are getting more and more kind of prevalent and ways to calculate those. So I can create a nice density map like this. I can create something called a kernel density, which creates these nice smooth curves. So instead of me looking at all these points, I can look at something that looks like this. But graphically, what I have here is that for each cell, I just create a density. Now with this density mapping, there's a lot of input parameters that I can set up, meaning the mask. Meaning, I just want to do it for the entire state. I don't care about the rest of the state or the rest of the country. Cell size. So how big is my cell? Do I want to store it at 6-inch resolution? Do I really need bare sightings at 6-inch resolution that I have my imagery with? What about, 100 meters? 100 meters might be good. And so we have this nice compromise between cell size, processing speed, all those other things that we deal with. If you're doing hydrologic modeling, you guys do it, what resolution or data are you working?
Right now, I'm working on 30 meters.
30 meters.
Oh, I'm sorry. I did 30 meters, and then now I'm doing a 10 meter. Not a lot of places have one.
No, definitely not. Not a lot of places have 1 meter stuff. And so cell size, output size, and Thomas, he came in when we're doing hydrologic modeling. The thing that you want is elevation, because where does water go? Down, wherever down is, and who's going to tell it down is the DEM, that digital elevation model that we were showing before. Now, how do I know what the exact elevation is over there versus there versus there versus there's someone out there checking it? Probably not, and so we're extracting it from satellite and LiDAR and all these other methods, and probably once in a while people go out and field check it and all those other good things. We have our search radius that we said before. our units, area of units, normalization and all that other good stuff. And so I can turn a map like this, which is deer vehicle collisions for Alamance, Orange, and Durham County, into a nice, pretty deer vehicle map that looks like this. And then what I could do is maybe count these by quadrants. Remember our quadrant analysis we did right after the midterm? I could do this, and this is the collision density that I can look at. So it gives me more granularity than just counting the number here. Because if I just count the number, it's like either a 0, a 1, a 2, a 3, or a 4, where these densities are going to be more continuous values that we have here. So we can go back and forth between these. Or I can count these by quadrant, where literally it's the only possible answers are 0 to 12, But it doesn't really matter. We don't need to calculate the collisions per square mile, because this square is the same size as this one, and the same size as this one, is the same size as this one. So these are really easy for the lay person, the average person, my mom, your dad, your parent, whoever else, to understand this map. They can understand this thing. And so from here, we can query out results. And so in raster data, we can query out results where that we can say, hey, let me find all the elevations that are more than 500 meters. Now, we can also extract data from these DEMs. And so we do things like hydrologic modeling is basically, where's all the water going to go? And you go, do you know Corey? Do you remember Corey? Corey was one of our former students, and he works in stormwater down in Durham. Yeah, and basically that's what he does, all the stormwater modeling and I think surface modeling and all that other stuff. So down at the bottom of the hill, how much water from the entire city is going down to the bottom of that hill versus the bottom of the other hill off of Alston Street down near the parking deck? Where's all that water going to accumulate? And how much of it is going to accumulate? What is the watershed for that? You go up the hill, you go down the hill, and basically right at Fayetteville Street, if a drop of water hits on the other side of campus, it's going to go sit down right at that football field and just basically sit there unless you've got your groundwater system that can get it out. So you got the big pipes versus the little pipes versus something that hits on this side of campus that goes right down to that elementary school right at rush hour. And do they have the pipes to accommodate to get rid of all that water when everything goes down that hill? So modeling is important, where we look at things like slope. What is the slope of it? Because now when you have slope, it's going to tell us how fast the water goes. And then that increases runoff and all those other things. And then we've got aspect, which the direction it faces. So we can look at derivation of these things. So this is what a raster query looks like. And then, like I alluded to before, we can do kernel density mapping, which makes them look nice and rounded. And then what we do now is we can now interpolate to raster. So we have our density mapping where we just turn a bunch of points into a raster map that shows higher and lower. We can make them red and blue and all that other good stuff that we showed before. And so it's got colors that go from light purple to dark purple, light green to dark green, and all those other things. But we can turn those into the nice little colors that we have, blue to red for temperature and all these other things. Now, the other thing that we do is interpolate to raster. So now I can do something called IDW, and I'll talk about some of these because some of these are truly most of these are going to be mathematical in nature. There's no AI going on with any of these things, but the way that we do them is slightly different. And so at the end, we'll talk about some really neat potential ideas for research, algorithm development, as opposed to applying these to like air quality and temperatures and all these other things here. So when we interpolate to density, we interpolate one of the fields, the PM value. You notice before, we were just looking at the locations of points and just counted the number of points right there. In theory, if we were doing things like crime mapping, we could have given homicides different values, like a 20 for a homicide and a 10 for a forcible rape and a 2 for assault, where we could weight those a little bit differently. But we don't do too much of this in class. What's the density of points? They're all going to be treated the same. Where with IDW, it's not. IDW and interpolation, we're going to fill in the missing values that may not be there. So we're going to create that weather map or that PM map or that rainfall map based on the existing values that fall in there. When I create a density map right here, I just count the number of values that are already there. And I go to the next cell and go to the next cell. And so if my cell side is 50 meters, I'm just going to go over 50 meters, go over another 50 meters, or go over a kilometer, whatever my cell size is going to be based on the projection of your map. And so you can see right here, this is my Z field is going to be my amount. I think we're looking at rainfall or temperature or something like that. And so when I look at the environments and the processing environments, these are all the things that go on in the background. So when you run stuff, these are the things I pay attention to that you all as problem solvers need to start paying attention to, meaning like, what's your output coordinate system? What is your processing extent? To me, I like to set up my masks to be the counties, meaning that when I run these interpolation routines, it could be for the entire country, but I just want to do it for North Carolina so it looks nice and pretty, even though we are calculating values outside of it. And I can set up my processing extent. Typically, my processing extent could be for the entire counties, or I can include it for all the counties, because when I make a map here, when I make this map here and I look at temperature, the temperature here and here and here is going to impact what's going on in North Carolina. Because remember, North Carolina isn't an island. It's not the island of North Carolina. So when I create this surface, in many instances, I might want to collect all the values around because they're going to have an impact on right here. In Rock Hill, the temperature in Rock Hill is going to impact what it is in Charlotte. Even though I don't want to show it in this map looks really pretty. And so our processing extent in our maps, in our masks might be slightly different. And so when I go to a climate prediction center, I can download this. This is the research that Steedrick. Remember Steedrick? Oh. This is some of the stuff that he did a long time ago. I'm always wanting people to like replicate that project, and no one wants to. And if I
Actually, I think that I'm working on flooding testing.
okay. Future climate. And if I remember, you did something with Thomas is here, and he did something with flashiness, right?
Yes.
Because a lot of times we don't really care about rain too much. We care about when it rains a whole lot and it can't percolate, infiltrate, and get flood and get out of its own way before it starts to create flooding scenarios. And so that word flashiness, I think, was pretty, kind of remember. How often did we have flashy floods?
I just did a 50-year. My time
Yeah.
was a 50-year, 2 years times.
Yeah. Yeah, and that was just north of Durham, right? So some of the rationale, and when I'm done here, we'll take our break here. But some of the rationale behind interpolation is that observations of points that are close together in space are more likely to have similar values. And as we move further from the observation point, there exists more variation in data. And so, like Caitlin alluded to, she had a good idea as predicting what the temperature was going to be in Asheville based on all the values nearby. And then that kind of leads into this third point here, where that the reliability of data as we move farther from known points will decrease. And so these trends with the data will not appear geographic, but mathematical, and the more points, the better. And so if you're working with like 3 temperatures, temperature stations throughout the entire state, you're not going to really get good predictions, especially when you start to bring in elevation. Because if anyone noticed, that max temperature for Mount Mitchell which was maybe only 50 miles northwest of Asheville, was 64 degrees. Everything else was in the 80s. And why? Because it's got an entirely different climate. The climate of Mount Mitchell, which is the highest point east of the Mississippi and the highest point in North Carolina, they got the same climate as like Newfoundland, Canada. It's cold, it's windy most of the time, even though it's just 50 miles northwest of Durham here. And so when we look at interpolated values, this is kind of what it looks like across place and space, in this case, one-dimensional space. And then we get into kind of two-dimensional space right here. So we have these known values, and then we create a surface that looks like this based on the existing values that we have. So you notice here it goes from 27 to 20. So in between here, it's going to be 23. It's not still going to be 27. It's not going to be 20. So you can see the gradation because this 27, this 20 is going to impact it most, but this 16 is going to have an effect on it. And so we're going to create these big weighted average formulas using these things right here. Like we said before, we would love to have evenly and equally distributed sample points here, but we know in reality that isn't the case. And so you can see here ozone monitoring in California, where they're located, and then the interpolated prediction surface that we have here. And so the thing that we also do in the input parameters that we have for interpolation surfaces are we can convert vector to raster where we have a mask layer, the type of interpolation routine. And pretty much for the rest of the class here, we're going to talk about the different types of interpolation routines. We have Craigen, splining, IDW, IDW2, something called nearest neighbor. We can get in, it kind of bleeds into this subject called Thiessen polygons, which are used in business. And so like catchment areas, you know, it's really big with hydrology where we have these things called watersheds. So we kind of look at the idea of kind of like travel sheds and things like that. But we can look at the power of the routine, the search radius, the output cell size, the output raster location. And so we can look at air quality after 9/11 based on these existing, you know, stations right here, the interpolated values of perception and whatever we're looking at there. Now, the different methods that we have. We have something called IDW, inverse distance weighting. And like Alondra alluded to before, we've already heard of this in cluster analysis when we said, what's the definition of a neighbor? What's my neighbor? I'm a cell right here. I want to figure out what my value is based on that one, and I'm kind of getting a little theatrical here. So I'm a cell right here. I want to figure out what my value is based on that station, that station, that station, that station. How many am I going to count? And so IDW kind of looks at this. Now, when we look at interpolation, we've got like 6 or 8 of these different things here. And so I would encourage everyone, since we're not really going to talk about that, we're not going to talk about spline with barriers and topo to raster and trend. I'm a big IDW person, but if you do some research, you might see that Craigen and splining are better for weather data than IDW or natural neighbor. I also like natural neighbor because, well, it's based on the natural neighbor, and it's also a calculation of a weighted average based on area. And so IDW basically says, well, you're twice as close to me, so your value is going to have twice as much of an impact on mine. Now, haven't we done this calculation before? Yeah. We did this with weighted averages. Now, how many is it going to pick? How many of these nearby points is it going to pick? And so within those, we can do, hey, I only want to pick the nearest 12. I want to do a fixed radius. So anything within 20 miles of me, that's going to be it. Anything, I want to pick the nearest 12. So when you look at that PM map for North Carolina, you got to be really, really careful here. And so we'll kind of look at this here. I swear I know what I'm doing. Okay. So when we start to figure out this PM here, particulate matter, you know, these are PM sites. Elizabeth City is way over here. What's the problem that you're going to start to see with finding the value, the PM values around Elizabeth City, up in the northeast part of the state? What's the big problem you run into? There's not a lot of nearby values. And so if I say, hey, give me everything within 10 miles, it's going to say, there's nothing within 10 miles, stinks to be you. Okay, the second thing is, all right, let me find the nearest 20. You know, we get to the nearest 20 here, we're in the middle of the state. You think things going on here in the Uwharrie Forest are going to impact that? I don't have much of a choice here. You know, I got a lot in Charlotte. I got a lot in Research Triangle. You know, I want to see, you know, the temperature at the zoo or the PM air quality at the zoo. I've got a nice circle of things all around the zoo right there. But I get out to these fringe areas right here, it gets increasingly problematic because depending upon the algorithm I use, IDW or whatever is purely mathematical in nature, but if we have slightly different slope right here, y equals mx plus b, we got a slightly different slope. They're not going to differ too far at the beginning, but they're going to differ a lot at the end, especially if we have to extrapolate those across large amounts of place and space. And so we just have different, and these are called input parameters. Okay, input parameters. And so we can use a first power one where it says if this is a distance of 4 and this is a distance of 8, we know that, and this is unknown value here, we know that this is going to have twice the impact of this. So when we do that weighted average, it's going to be 0.5 times 1 times whatever we're going to add it up to be. Remember we did that weighted average? And our weighted average were pretty simple calculations that we did in Excel. We can look at the difference between IDW1 and IDW2. Ooh. And so now with IDW1 versus IDW2, meaning if we do IDW1, it's just first power. Okay? This one is going to have twice an impact of this one. If we do IDW2, where we set the power to 2, this is going to have 4 times more of an impact on this than this. So the weight is going to be 4 to 1 or 2 to 1, depending upon the power that you set. Now, what's the difference between these, between IDW1 and IDW2? We're doing the same exact calculation. The one thing to me I see difference is that the values nearby are going to have much more of an impact than values that are far away. So if you see some like 102s or 107s, they're really going to be fleshed out with IDW2 versus something like IDW1. Okay, the other type of interpolation routines we have are called splines. It creates a surface that passes through control points and has the least possible change in slope. Where we heard the word slope before? Last week, right? Just last week, we were talking about regression, right? Y equals mx plus b. And it did this whole thing called ordinary least squares, where we basically created a slope that had the least variation between the actual values and the predicted values, which we just let ArcGIS Pro and Excel just magically do for us. But we create a minimum curvature surface because in theory, like we said before, like Caitlin alluded to, we're not going to have a big change in values as we move from one to the other to the other. This has big problems where we have little data. And so we might run into problems. We have steep gradient in data poor areas because of the algorithm it uses. So if you run splines for some areas, you might get like negative PM values. Can you have negative PM values in real life? No. Does the computer know that? No, it's just a dumb computer that does whatever you do with the data that it gives you. That's all it is. I hate to call it dumb, but that's really all it is. Okay, you're the one who uses it. And so you're the one who determines what algorithm it is. Because if you were to go to a conference and show, hey, look, this part of the state has negative PM values, what do you think people are going to say? No, I don't think so. Okay. And so make sure you use an algorithm. And also, when you use these, hey, maybe for air quality, we have different, one of these algorithms is going to work best. And so this is what a spline kind of looks like. It kind of looks like a kernel. It's got nice, pretty values right there. But you can start to see it gets really ugly really quickly as you get far from known data points. And so this is precipitation in Idaho using IDW versus spline. And one of the things that I want people to do at some point in time is, hey, we have known values. We can figure out what the difference is between these. What's the difference between IDW and spline? And then this is what Stedrick did. Where that we went and did. This is a former master's project by Stedrick. Does he still work for the city?
I think he still works.
Yeah, he works for the city and he does some sort of GIS type of stuff. I don't think it's purely GIS, but
No, he started off with like the stormwater.
yeah, he started off in stormwater. And so what we did and what he did was he removed 10 random readings of temperature range from our field. And basically what he was looking at is what's the difference between IDW first order versus natural neighbor versus other algorithm techniques? Now, the trick is we had to figure out what the actual value was at that point. So we had about 100 stations and we removed 10 stations. And these are the 10 stations that we randomly removed. Why would we randomly remove those? What we start to do is measure accuracy. What's the definition of accuracy? What is accuracy? How accurate are these things? My answer on the test versus what would you give? Or would you give on the test versus what I say the answer should be? So we remove these because these are quote unquote the right answer. These are the right answer right here. And so we ran the interpolation routine and it gave us 18.7, but in reality it was 18. When we ran the first order, it said it was 22, but it's really 27. And so we ran the interpolation routine for 90 points. We removed 10 because these are our right answers right here that we can compare the right answer to what the routine gives us, to what the routine gives us, to what the routine gives us. And so we could figure out, hey, what has the largest variation? Okay, I have this little thing here called delta. Does anyone remember what the word delta means in math class? The change in. What's the difference? Hey, we want as little change as possible, right? Now, some of these, so we want as little change as possible. So you can see some of these, wow, look at the delta in these right here. It said it was going to be 22, 22, 21, but it's really 27. So something might be going on in Bent Creek, maybe based on elevation or lower elevation or just a bad day or something else. But you can see what the actual are versus predicted values. Have we looked at the difference? That's what we call a z-score, right? So we can calculate z-score. We can calculate averages, means, medians, modes, all this other stuff so we can start to compare some of these things. So we can go do some really basic statistical, descriptive statistical analysis across these various stations right here. And I thought this was pretty neat here, and the homework is going to kind of look at that. Now, if we want to, we can make line features out of these, creating isohyates, and so lines of the same precipitation, isotherms, lines of the same temperature. And so within these geoprocessing applications for, I think it's for raster, but they also might be available in interpolation. We can look at these as well, because what we look at here is how do we find the difference between these, known points, existing points. A couple others that I will mention, we have something called Kriging. It looks at deterministic model. Variations within our attributes are neither random nor deterministic. And so random arrows are recognized with regional trends. It seems the distance and direction between sample points reflects a spatial correlation that can be used to measure the variation on the surface. So these are some words we've used before. What I like to do is just click the run button and see what it gives me. That's what I do. And some of these will be truly interpolation. Some of these will be truly interpolative, while some of these will be extrapolative, meaning that I start calculating things out here, and I think one of these, like splining or Kriging, is going to say, I don't go out here. Why? Because I don't know the values. It'll only calculate it for within the extent of these red points. Because I said, I don't do extrapolation, meaning I'm not going to go out in this direction. I'll do this, I'll do this, I'll do this, I'll do this. I'm not going to go here, I'm not going to go here, I'm not going to go here. And so I think with the spline or the Kriging, and Kriging is just named after a person. With the spline or the Kriging, it's not going to be truly extrapolative in nature. Okay, and so the other thing the other one that I really like, which is this mathematical in nature, is something called natural neighbor. So the algorithm by natural neighbor finds the closest subset of input parameters to basically weight them based on the proportion of areas within the value. And so we're almost done here, and then we'll kind of stop in a second here. But if I'm looking at the cell value right here, it'll create these bisects. between all the other existing known points and then just calculate the area, proportion of area with that value. So once again, that's just going to be a weighted average based on the percentage of this weight, percentage of this weight, percentage of this weight, percentage of this weight, and the percentage of this weight based on these, what we call Thiessen polygons. Has anyone heard that term before, Thiessen polygons? Basically, this is a Thiessen polygon, which is everything in this polygon is closest to this point. Everything in this polygon is closest to this point. Everything in this polygon is closest to this point. When we start to draw these, basically midway, the lines in between the points, and then we start intersecting them and then taking away things. And so when you see like service areas for McDonald's and Walmart and all those other things, this is what we're looking at, service areas right here. They're kind of like watershed versions of businesses. And so when we start looking at Z's and all that other stuff, we can kind of look at those. But during the break here, and it's 6:11, so we'll come back at about 6:23, 6:24. We're gonna just start opening up homework number 8, and then tomorrow I'll kind of post the homework and all that other good stuff. And I'm gonna spend a few minutes here with Thomas. All right, how you doing? Good. All right, cool. How's the daughter doing? She's doing good. How old is she now? She's
6, first grade.
okay, first grade. Oh,
I don't normally come down Austin Avenue going home. Today I was like, come down. I was like, just turn right here.
okay. Good. Where'd she go to school? Around here?
Yes, she goes to yeah, it's closer to like South Point, but it's still in the area. Yeah.
Parkwood or something like
Yeah.
that? My wife's doing some work down at Parkwood in the next couple of weeks, so.
Exactly.
Yeah, she has to map all the places around here and one doesn't make sense. Oh, goody, good,
Yeah,
good.
the twins. I saw the pictures on this. That was the
Twin fest.
twin fest. Yes. How was that?
Just a bunch, twin, 2 to 102, so.
Yeah.
Yeah, I haven't been doing too much of this. So are you working over at RTP?
Yeah, I'm in RTP. I'm at the main building. I'm only there. I'm only on site on Wednesday right now. Really trying to figure out what's happening in November. Just to go shut down right now. We're gonna see if they're gonna approve a budget or not. If not, me being a contractor. Contractor.
Okay.
So me being a contractor means laptop don't get paid. So I'm hoping that they, November 17th is what we but yeah,
Wish you guys would get there, but they have no problem getting themselves.
yeah, but it's definitely it's fun. I do use ArcGIS, I use Pro quite often, especially when they raster data. I'm dealing with raster because
Okay.
elevation, PMs, but also looking at presentation. I'm still conscious, not grass and HMS, which I put on the resume that I had one class of it. Saw that and ran.
Okay, what's heck at HMS?
So HMS is civil engineering and modeling.
Okay.
Had it with Dr. Mahondra.
Okay.
He had a different class with him. If he's still coming sometime or.
Who's that? Yeah, he's still
So, oh yeah, I think we did a class with that. I want to say we might have did one teaching hydraulic. The graduate course went out to I think we did like 2 assignments, which is all long. But like to do it now, it's like such a headache, such a lot of errors going back, trying to figure it out. Yeah.
Different agenda, so.
That's probably that's what I was looking for. When I actually applied for the job, it was a climatology, like studying climate stuff. And then they switched the position over to hydrology analysts.
Okay.
So it was like, okay, this one I did the dynamic, flash chemistry.
Yeah.
So that was like, okay, we kind of understand there's something. It's been pretty good. Some things that I kind of knew, and it was just like, oh, it's just fresh. I think by that time I was out of school. Here, school. And I was graduated from grad school and from grad
Okay.
That's how I would
So you work for Oak Ridge as student?
contractor and then contractor.
Okay.
5 years of bridge
Okay.
and she was like, yeah, you know, a lot of people that come in as contractors, but hard to get on that. Actually,
Yep. Oh, I worked for a contractor for the military. Like, probably like 2/3 of them were contractors.
yeah, so there was like this a lot of hard, but then there's also they have different types of contractors. Yeah, like one of the guys that's in my building, he's telling me he was a contractor for quite a while. Then he went through what's called pathway, and once he got done with the pathway, he position luckily the position was open. And he had all the jobs, so they just
Good. Yeah.
and the same thing going for the person it's where I work under. She's like her PhD in hydrology and climatology. So she was like, that's how she was both overall, which is what I am. It's student contractor, and she was overall, which is part of it.
Yeah. I've heard that. Yeah.
Yeah. So she worked both sides, and then she became actual. So, but yeah, it's.
Yeah, they pay real money and so like enough to live off of and all that other stuff, right?
Oh yeah.
So is it more than Duke or?
Definitely more than Duke,
Okay.
and more than I went from Duke to USC.
Okay.
Because I actually was the data coordinator
Okay.
at USC. We were just doing everything USC. I was working at planning. I was working at testing. So people were coming in, just to throw nurses to take it back, and they would come. After they were done with their back, they would give us the charts. It was very simple, but during the time I was just searching, I was trying to get on it for the city in there. Everything was just like, no.
Yeah, like Corey got real lucky, we sat down and we like wrote the letter together and we made sure all of the keywords from the listing position were in there. And he's told me a couple times, like he's got a couple promotions, so basically when you see an open job, it's just, they might be promoting someone from within. And then they're gonna open up that, tax one position, which you're probably gonna be.
And that's what I actually with a lot of times too. Because I was talking to Steve, I was like, I just want to get a job. And then I also talked to Nelson one time. I was like, yo, I just want a job. Just, let me know if something comes up. And Nelson, he's pretty good. It's like, yeah, I'll let you know. Because he was.
Yeah, they're always, they just hired, if you remember, what's his name, Rogers Mitchell? He was an undergrad and he worked in utilities and he just got like entry level position over there. And because I speak to the guy over there and he's been promoted at least once, because I think.
Then he went to NC State and he took over the
Photogram
for his
stuff,
family.
yeah.
Yeah. There's actually a group that he created that's programming. So it's so broad. It's crazy. I never, even when I was here, I never thought overall.
Yeah,
That information.
that's, they're good, they're real good.
Well, so I work under, I have a mentor, she has two basically students contracts. And the other guy, he went to the Nicholas School of Environmental Science.
Okay.
And he was just telling me, he was like, yeah, it's kind of like they have this thing with EPA or at least it seemed like it was, you know, a lot of their grad students like it that way. I was like, oh wow, I didn't know that. That's NC State. He said he went mostly to work on DOT. He did that for a while. Which works over as a whole. But yeah, the majority of us, that's the geospatial department. If you're not full life feds, we're just we see practice or we see postdocs or people working on their PhD. So, I mean, still. But I would tell you something you got it. Have you heard of
Yeah, I heard of it. Yeah.
So that's part of the team. Yeah, so I'm trying to get the flooding information in correctly so they can update it on so okay. A lot of CNET, mythology stuff that that's just one thing. Or a student, but they're looking at wood pellets.
Oh, yeah.
They're looking into wood pellet farming. So that's the thing. That's the guy who has vehicles. So, and the reason why I know about those projects is because they're going to talk all of them together. They run a CNET, this is a succession of those area. And this is what flooding is about. This within the facility. So it's all there's a lot of that information goes to those levels.
You're doing like real science stuff. That's good.
Yeah, it's definitely, and that's why I pay it because I think of GS. I think I GS 11, GS 12.
GS 11 and 12? Pretty good.
Yeah.
Oh, wow. Okay.
Yeah. It might be GS 10.
It's still pretty good.
It's still pretty
Yeah.
good. It's
So well good. Yeah.
I don't want because my program is for 5 years with almost this year is here. So hoping start all over the process again. But my she was like switch. She was basically jump to the organization. And I was like, well, okay. She's like, hey, you start with me this year. Next year, you decide you want this gasoline. But
Just want to stick around.
yeah, stick around here. I get onto the geospatial team that for like a more geospatial. I did have an interest in hydrology, and I put in that. So they was like, oh, okay, cool. I should have had it in years. That's just a job.
Best way to learn, I guess.
It is a good way to learn stuff. You said it's like I'm just starting to get practice. Yeah. It's HHS, so what I was doing. I was doing but I reaches for work. I was doing the reaches and stuff like that. So I would do DMs. That's what I said. But HHS so I would do fly house under 25th. It's just one button. That's error messages. Yeah. Yes. We had this one still in some here. The LiDAR She should have got pretty good at first. So that's the site. Download. So then send an email. They was like, oh, okay. And they sent us the same blocks. I got number to it and everything. When you open it up, it's the same issue.
We're talking about 2 minutes. 2 minutes. Open up exercise E.
It's the same.
Yeah.
So it was just the same issue. That's what I'm trying to do. It's funny. Just what we did. I already had 10 years before studying. They want to that's about 2 terabytes. That's enough space. It's just how it's.
Yeah, oh yeah. You start working with scratch, gets ugly quickly. You put your guy John Joyner, he's been wanting to do some stuff with us and send some people over our way. So. Yeah, this guy might be out of Atlanta, but they're over looking to do stuff with us here. Let me get a picture of you out here just so I can post it to our Instagram quick page and stuff. So I'll post it. Well, appreciate you coming by. We're gonna start up class here. So, no, thanks for coming by. It was see you longer. I'm right. This is living proof that you can kind of, yeah, be like him. Yes. All right. Thank you, Thomas, for coming by. Yep. That good guy. He spent years working in the. So we're back here. Sorry, I took a little long. We had one of our former students, Thomas, come by. He lives locally, and if you heard a little bit of his story, he graduated in like 2013 or so, and he ended up getting a job with what did he do? He got a job working for Duke Hospital and then UNC Hospital, and kind of just didn't get a job doing it in the field. So he came back and went to school at night, worked full time, has a kid, went to school at night. Now he works for the EPA, and he was saying that he's a GS 11. Now, what does GS stand for? Those of you, anyone know there? Any of you kind of joining us online? What's GS stand for? Stands for government services. And so basically that's like the pay scale for GS folks. Like, you work, you're a teacher in Wake County and you have 3 years of experience. There's a certain amount of money that you make here. So based on like cost of living and all that other good stuff, you can, so GS 11 pay scale. This is what we're looking at, like, GS, like 59 up to about $77,000 a year. Pretty good. Pretty good, especially for someone who's only been in the workforce literally like a year as a student intern. And student really isn't the right term. He's not a student intern, but it's through a program called ORISE, which is Oak Ridge National Lab. And so he said he works as a contractor. So if a lot of times if you work in federal institutions or military bases like I did, you work for an actual contractor because EPA, the government, military, they don't want to deal with HR and sick days and all that other stuff. So they'll do things like RFPs, requests for proposals, so that companies can bid for it and say, hey, we'll put 3 positions here for $400,000 or whatever, and we'll deal with the HR and the retirement and all that other stuff that you don't want to deal with. So, a lot of times you hear the word contractor before. So pay a little bit more, but there's a little bit more volatility. So we just talked about the idea of him having like a 5-year contract, and you can revisit projects every year. So there's a little more volatility, so that when that contract comes up, or ORISE loses that contract and say, hey, we want to hire someone else, you might have to pick up and move or do whatever. And so it was really good to see Thomas, and I think he was one of our big success stories, because he's just graduated with his undergrad in like 2013, and just like, I want to do this, and he came back to grad school, and we got him done quickly. And like we were saying before, he did something called flashiness. And I don't know much about flashiness, but a lot of times when it rains, we don't really worry too much about the rain, because it percolates and infiltrates into the ground. And then we've got all of our stormwater set up, so when it does hit impervious surface, it's gonna flow in the right direction wherever gravity tells it to. And then we model it so that we've got pipes and sewers in the right places that can take the water off to some magical place that we don't have to worry about again. But when we get high volume rain events, that's the problem, meaning that we've got so much of a catchment area that it can't flood it quicker than what we have those. And so one of the things, and this deals with impervious surface as well as the actual rain event and topography. And so some of the issues that we run into these days with hydrologic modeling is that, what's the problem? We got things like, we get 100-year floods. Have we heard the term 100-year flood before? It's a flood that's only supposed to happen every 100 years, but we might get 3 out of the last 5 years, we have a 100-year flood. What is the chance of having a 100-year flood every 3 years in a row? Infinitesimally small. And so to me, part of it is the actual data that goes into making these flood maps is changed just because of the changing tenor of land cover, as well as climate change. It's so volatile, unpredictable, and then other things like PM. And so a lot of times, if you notice, one of the big jokes up in New York with the football games recently was like, hey, we finally had a weekend where it didn't rain. Well, why does it rain on the weekends?
Is there a specific answer?
Yeah. Why does it rain? Yeah. Why does it rain on the weekends? Yeah. You notice it sometimes does. Because when you put junk into the atmosphere, like this microfine material from car exhaust and things like that, it creates a condensation nuclei on which water droplets can condense. And so when do we have most of our traffic? Monday, Tuesday, Wednesday, Thursday, Friday, and eventually we get enough condensation together that it starts to fall on Saturday and Sunday. Just learned something. So, okay, that's really true. For exercise number 8, this is the last of our exercises. We've got in the Esri training site, we have something called spatial interpolation using ArcGIS Pro. So we're just going to sign into our ArcGIS Pro. We talk about deterministic and geostatistical methods, stationarity. But what we're going to look at here is GIS data here. And let me look real quick. Let me see if this thing is actually open here. This thing is still not working here, and this thing is down here too. All right, and so we'll do what we can during in the next couple of hours here. So what we're going to look at here, and what I showed here, we are looking at EPA values right here. So in theory, what we've got going on is in the red squares is that we've got stations. We've got monitoring stations throughout the state. And then these black triangles right here, these are just cities that I'm going to try to ask people, like, what is the value here using one method versus another method, using another method, using another method. So as you can imagine, if we zoom in a little bit right here, we zoom in a little bit right here, I've got Durham City downtown. I've got a station just to the north right there. As you can imagine, regardless of whatever method that we use, the value between the actual reading and the city are going to be relatively close to each other because they're really close. If I'm standing, if I'm half a mile away from the station that reads 85, no matter what method I use, the temperature is probably going to be close to 85 no matter what. Once we get further away, that's where we run into things, especially when we deal with these purely mathematical surfaces that don't know that PM can go below 0. Okay, so we have this. If we really wanted to, we could right mouse click and we can click on symbology. And so I can make these kind of graduated symbols. So I can say, all right, let me look at not graduated colors, but graduated symbols right here. And the field that we're looking at here is called average measure value, because all I did was I went and averaged the PM values over a 6-month period. And so I could kind of vet out some smaller ones, larger ones, or whatever I wanted to, but it's called average measure. And so I could see the bigger versus the smaller right here. And so when I look at this map right here, I can see these bigger dots represent the higher PM values. The smaller dots represent the smaller PM values. And when I mean small, it's like 7.7 up to 8.7. And this is like parts per million, or it might be parts per cubic meter or something like parts per cubic meter, I think is the measure. And Benjamin tried kind of telling us how we get those measures previously. And so you can see where it's high and where it's low. So around the Charlotte area here, out in these areas right here, they are a little bit higher. But when we look to the RTP area, our PM is relatively low. And that's just kind of a proxy for air quality, even though it kind of takes into account temperature and all that other good stuff. And so what I want us to do is just kind of start working on this a little bit here, and we'll do it together, where we'll probably go through and do IDW and spline, make sure we do this correctly. And then the other thing that I want to do is I want to do something called extract values, because when we run IDW surfaces, we run spline surfaces, Kriging, and natural neighbor, it's just going to give us a surface. Well, I want to know where it is right exactly there. And so I've got another routine right here called extract values to points that allows me to do that. And we'll see what that looks like. So we can go back and forth between our vector and our raster, because in theory, what we want to do at some point in time is we can create these nice little automated models. And I talk about these a little bit in 4010. And then if anyone's taken the introduction to data science next semester, we're going to spend our whole first week on just automating processes. So instead of me pointing and clicking and running and doing all these other things, why don't I make a model? I click a button and it just goes and runs it, so I don't have to do this over and over. And so the first thing we're going to do is we're going to create an IDW surface. And so what I'm going to do is I'm going to create an IDW inverse distance weighted surface for the entire state. Okay, for the entire state. So I'm going to get out of this catalog right here. And so I'm going to fill it in what's up here, what's over here, what's over here. What are all these values right here? Because right now I only have 35 separate values. So I want to see what it is in Havelock versus Wilson versus Sanford versus Asheboro. In theory, I want to look at it for the entire state. So I'm going to click on my geoprocessing. Okay, and I'm going to get this little toolbox that comes up to the right here. And then I'm going to click on toolboxes. And I have this thing here called Spatial Analyst. So Spatial Analyst allows us to work with raster data. Now here, in this case, we're going to create raster data. And you can see I've got groundwater, hydrology. And so you notice right here, and this is kind of neat here, if I click on hydrology, it's got whole sets of hydrology tools. So if you heard me talking to Thomas, this is where he lives right here when he uses ArcGIS Pro. We want to model surface water. That's all we want to do is figure out where surface water is going to go based on what? Based on the elevation and what's coming from it. Because like I said before, we're at Fayetteville Street. Fayetteville Street kind of splits the campus in half, and it kind of goes downhill in one direction, downhill at the other direction. So it kind of serves as a crest. So in theory, kind of Durham is actually right in the middle of a couple of different watersheds. And I think it's like the Cape Fear River and some other river. It's pretty neat, like downtown Durham, right around here, where water goes in one direction versus another direction. And so Thomas kind of lives right here where we look at stream links, watersheds, fills. Flow accumulation is a really neat tool that figures out at this street here down at the bottom how much water is going in based on the elevation and what's below it and all these other things. And so that's a pretty neat space here. But what we're going to look at here is interpolation. So these are the different interpolation routines that we're looking at. We've got IDW, inverse distance weighted. We've done this before already. We've done it before. Okay, IDW. Basically, we did it with clustering where, okay, what's my neighbor? You're closer to me. You're more of my neighbor than you further away. And so we're going to look at the parameters in which we can do this. And so we can set up different interpolation routines as well as different parameters so we can change these. So if people are interested in kind of looking at some of the theory as to what's the best interpolation routine, I would be totally open to that because it would look good for you and look good for me and kind of bring upon the research that Stedrick, who's one of our former students, is doing. But we're going to click on IDW. And then we're just going to look at the input parameters that we have right here. So our input point features are going to be what? They're going to be our PM sites. Okay. In my Z field is going to be the average measure value. Okay. Because you notice it's got three possible values. It's got latitude, it's got longitude, and it's got the average measure value. And then basically we have the population at the city there. We don't worry about that. The average measure value. Okay, the output raster, if you've unzipped this correctly here, it's just going to store it wherever you saved in that GDB, which is a geodatabase, and we call it IDW PM sites 3 or whatever it's called here. Now, the output cell size, we're going to just leave this, but this output cell size is the resolution, how wide, the resolution of each cell. Now, these units are going to be in degrees. And so 1 degree is equal to about 70 miles. So we're looking at the order of like probably 50 meters or something like that. And so even when we make this data here, we're going to be working with a lot of pixels. Now the power. Okay, what kind of power do we want to look at? We could look at 1, 2, 3, 4. I'm going to put it at power of 1. Which basically means that if you're twice as close to me, you're going to have twice an effect. So remember when we did that weighted average? It's going to be a big, nasty weighted average calculation. And what we're going to do for every single cell, and I'm kind of demonstrating it right here, for every single cell, we're going to run a weighted average based on the nearest stations and then all these other parameters that we're going to set. Now, my search radius, I'm going to set that to be variable. The number of points, we'll make it 12 points. It's like the nearest 12 points, right? So now it's going to get really weird once we get out to eastern North Carolina because 12 points is going to be really far, which probably won't have an impact. But if I set a maximum distance right here, and I can set this in degrees, like 1 degree is equal to about 70 miles. If I were to set this to like 1 degree, meaning I'm only going to look 70 miles away. To circumvent working with these nasty numbers is that I can project these to North Carolina State Plain, and the base unit for North Carolina State Plain is going to be in feet. So I can set these to, 5280 times 100 or whatever miles that we're looking at, the number of feet in 50 miles or 100 miles or whatever. And so these units are extraordinarily small just because we're working with degrees. Degrees are really big units. And a degree is an angular unit that we're working with here. Because when we download this EPA data, it gives it to us in degrees, and I didn't go through and change it, even though I displayed it as such. Number of points. What's a good number of points to have here? And I'm kind of picking on Alondra here. Is 12 good? Yeah, I think so too. All right. Why wouldn't we use 1? And you're right, about 12, but why wouldn't one be a good idea? Yeah, it's for the nearest. If we just gonna do it for the nearest neighbor, then if that's got a really high or really low, or if two things are almost the same distance from each other, and we say nearest, but it's based on the one that's 1 mile away instead of 1.1 miles away, they both almost have equal impact. And so when we look at these input parameters, there's a lot of ways we can go here. Now, environments, look at all this nasty stuff we've got going on here. Okay, now under coordinate system, I'll just click on the current map right here. The output coordinate system if I want. Cell size, I'll leave that. But I'm going to change the mask to North Carolina counties because, to be honest with you, do I want anything else outside of the state? No. Okay. And then under processing extent, I'm going to click on default, meaning that if I happen to have other stations outside of the state, I would want to include those, right? Okay. Isn't any PM values over here going to impact North Carolina? Yeah. So a lot of times I'll leave that as default, or if I wanted to, maybe I might click it as the union of the inputs, meaning everything, have everything. Union meaning the most, where I use the spatial or instead of the spatial and. Now, the mask is going to be this here. Okay, and now when I'm ready, let's run it. Let's see what it does, because all it's going to do is create a weighted average of all of these things here. I see an output cell size. Oh, cool. Well, look what I got here. Ugh. What happened? Yeah, it only went where? Why? What did I click on? The union of the output, the union of the inputs. Now, what were the inputs right here? I got my cities all the way out to my nearest PM station. And this might work for you right there. It might work. That's okay. And so for my processing extent, I might change it to, let me change it to NC counties. And then let me run this thing again, just for the heck of it. I swear I know what I'm doing. Yes. And there it goes. And so you can see the difference between the processing extent, and then I just change it to NC counties. So it's going to go and create all these values here. Now, what I really want to do here is, and you can see what these values are. So these white areas using IDW, they're between 10.53 and 11.4, where these areas in green, 7.8 up to 2.2. And so I could figure out where it is in Asheboro, where it is down in Wilmington, where it is in Havelock, where it is in Elizabeth City, throughout the entire state. So when you look at a weather map, this is what you're doing right here. You're running an interpolation routine. Now, what I want to do, and as part of these answers here, what I want to do is I want to figure out what the exact value in Asheboro versus Boone versus Durham versus Havelock versus Hendersonville is right here. So I have a separate layer right here. I've got a separate layer right here that I want to do this for. Okay. And so if you notice this right here, if I sort ascending, so I've got these kind of 9 stations right here that I'm going to go and fill in, and I can cut and paste and do all that other stuff when I want to at some point in time to do that. Now I've got another routine, and I mentioned it here, and it's called extract values to points. Okay, extract values to points. How do I find that? Well, if I don't know where to find it, guess what I can do? Up in the top under geoprocessing, I can do extract values to points. And what's it say here? Extracts the cell values of a raster to a set of point features and records the values in the attribute table of an output feature class. That'd be really good, right? So I'm going to click on this one right here. And so what are my input feature points? My NC cities. What's the raster? the thing that I went through the trouble of creating right here, which is this IDW Sites 3. And then I got a brand new feature class right here. And I've got these other options here. I've never used these before. Interpolate values at the point locations, append the output. And so it looks like I'm going to create a brand new feature class here called Extract NC Cities 2. And we can call them whatever we want, especially something that's going to make a little bit more sense. But now, let's see what I got here. I got a brand new feature class. So this is a little different than your joins and your spatial joins where we're just appending things. So now I can open this thing up. What do I got? I've got the name of the city, and let me go all the way to the end. I've got something here called the raster value. So now when I sort ascending, freeze or unfreeze field right here. Look what I have here. This raster value in Ashboro is 9.55, 8.09, 9.32, 9.66. Can we plop those into a table? You bet I can. And if we do data science class, and maybe I'll mention it a little next week, we can also automate this process. If you really wanted to, what do you think you can do? You can, watch this, Control C. Me, I hate typing. I will spend more time cutting and pasting than I will actually writing stuff, okay? Because the more that you write, the more you have a chance of screwing stuff up. Okay, so I might, oops. Not oops. I didn't mean oops. I meant copy. Paste. And now what can I do here? I can just go copy everything that's sitting right here. And everything that's sitting right. You might have to play a little bit with it right here. There we go. So I just, those of you following along, what I did was I ran the extract value, and all that extracted value does was whatever the raster value is right at this point, I'm going to extract it. So whatever the value is right at that point, and all it did was give me the feature class again with the same fields, but it's got this little thing called raster value right here. And so if I were to look at, say, Durham, the point at Durham right here, okay, if I were to click on the raster value for Durham right there, somewhere amongst this stuff here, if I were to click on the raster value for Durham, I bet you it's going to be 9.32613 based on this interpolation routine. Now, what I'm going to ask us to do is, now you're going to run and do this again for spline. And you're going to do this again for Kriging. And you're going to do it again for natural neighbor. So the only thing I would suggest and be aware of is make sure you do the same thing every time. Leave the default processing speed. So we'll go to spline. Input features are going to be what? It's going to be the PM sites. Our values are going to be the average measure value. I'll leave the outputs for rasters, and then under environments, I'll just set it to the current map. The processing extent will be for NC counties because that's what we did before. And then our mask is going to be to NC counties. So now when I run a spline, a different interpolation routine, let's see what you get. There it is. Now I got a slightly different routine. Now, over here in the right, you can see what I've got. I've got negative values right here. And then I've got really high values like 16, which probably aren't possible. So it saw that it was kind of increasing as I went in this direction. So it probably just kept increasing more and more. It started decreasing in another direction. so it decreased more and more. And so you can see this spline, totally calculated surface. We're going to do the same thing again. And now we're just going to pop these values using extracted values for the spline, for the crag, and then for the natural neighbor. Now, for number 2, it says, what's the range of values for Durham? What are the range of values? So now we can put these in Excel. We know what the word range is. So what I want for the next question is, what's the range of values between IDW, spline, crag, and your natural neighbor? What's the definition of the word range? High minus low. Can you calculate that in Excel? I hope so. Okay. Maximum minus minimum. So now we can look at the range of values between these. Okay. I bet you Durham's going to not have a high range, partly because the algorithm used, mainly because the value for Durham is right next to the station. So no matter what station you use, the routine isn't going to get too far off kilter as it would in something like Havelock. These are really, really neat things that you can do here. And so what's the range of values? In a well-written, concise justification, briefly describe which of the 4 techniques worked best and why. And so what I'm going to ask you to do is do an assessment of each of the techniques. And so that's what I'm going to ask you to do. The next thing we're going to do is we're going to create a density surface. So we're going to calculate density surface and set it to be 5 miles. Okay. So now we're going to do something slightly different here, and we're kind of almost done, because now we're going to create a surface of deer vehicle collisions. Okay, based on the known values. So hopefully we're at a point in time here where we've created 2 interpolated surfaces. We've got one surface versus another surface. Okay, 2 different surfaces. Now, some of the things that we can do in ArcGIS Pro is that we can subtract these surfaces from each other to calculate the differences between these 2 techniques. But we haven't done this, and you can learn that in raster class or revisit some of the things that we've done before. And we can throw this into a model so we can automate this entire experience. So, just think of all the ideas that are running through your head. It's kind of, to me, it's kind of exciting. To you, maybe not, since you just want me to stop talking, hopefully. But there's a lot of neat things that we can do there. Now, the second part of this is that now I've got deer vehicle collisions, because I really want people to differentiate between these, because now when we create a density surface, we're really not figuring out what the value is right here or right here or right here. Is that we're zooming in for this cell right here, we're calculating a 5-mile surface, and then from there, we're creating a 5-mile surface, and then from there, we're calculating the density of those right there. So even though this area right here might not have a lot of, and I'm kind of zooming in right here, there might not be a lot of deer vehicle collisions right here, but if I look within my 5-mile surface, there might be. And there's some good things about that and bad things. I'll mainly focus on the good, where that if we're looking at block groups or something like that, and there's a block group right here that doesn't happen to contain everything, it might get a value of 0 when we run a spatial join, but when we run density analysis, it's going to kind of score higher values just because of the way the lines are placed. And so the same thing with, say, quadrant analysis, where it's truly a count number, a point and polygon method, where in theory this density is a little bit more, it brings into the account of neighborhood, where that this we use these count methods and spatial joins with these other things. All right, so without any further ado here, we're going to go to our geoprocessing that I just got rid of. And then under spatial analysis, we got something called density. We've got this kernel density, which basically creates these little bit more of a smooth curve. So it's a smoothly tapered surface to each point or polyline. While we have kernel density, and then we have point density. So under our point density, my input features now are going to be our deer collisions, our cell size, okay. And so now our cell size is going to be what? I'll leave the cell size as this, but what is my radius going to be? Okay, I'll leave this cell size like this, and we can kind of revisit this because I assume these are going to be in feet, in meters. This is this is like 2 miles, and so a lot of times we'll leave this. And so, what do we have in feet here, and what does the input parameter say? It says the output cell size. Use the default value for the cell size and set your circle radius to be exactly 5 miles. Since we're working with feet right here, okay, we're just going to multiply 5280 times 5. Okay, and I'm going to bust up my phone. And so I'm going to do this little calculation. So 5280 times 5, 26,400. So 26,400 feet. And so basically, if I run this and there we get a cell size that has a value of 0, that means within this cell, there are no points within 5 miles of it. Okay, no points. Because we're going to go in square units, aerial units are in square miles, and it creates density units and all that other good stuff. Under environments, we'll do the same thing what we did before. And so we'll set this to my current map, which is a state plane, which just measures things in feet. And then cell size, we'll leave that. Processing extent, we'll set it to be NC counties, because I'm not sure exactly how this algorithm runs. And then we'll mask it at NC counties as well, because I don't really care about the density outside of the state. And I like these nice, pretty products that are clipped to the state. But like I said before, when you run CRY or Natural Neighbor, even though you set your processing extent to be counties, it might not do it because it won't do extrapolation. Okay, and let me run this thing. Cool. Now look what I just did here. What does this map have? So instead of looking at all these points, what do I have here? What do the darker areas mean? Higher density of deer vehicle collisions. And so we look at this area right here. Look at this purple area right here. And I'm pointing out this purple area right here. And I'm going to put Alondra on the spot here. So you see this purple area right here. It doesn't have any deer vehicle collisions within it, but why is it still purple and why does it still have the highest? Who wants to help her? Anyone else want to help her here? And the question is, it's got no points in it, but why is it still so high?
Would it be because it's got so many points within a within the radius?
Yes, it's got so many points within the radius. And those are the things that I like, because remember, when you run quadrant analysis, if it's got nothing in it, it gives you a 0. And so now why did I set 5 miles? I don't know. That's where the deers go. To be honest with you, but I think the deers just live in my backyard and come out and eat all my stuff or whatever there. So that's why we have those. Because I think a lot of times people get a little weirded out when they see these. Now I could set the deer vehicle collision values to be equal to 1 mile or 3 miles or whatever. And you can see some places here we truly have some 0 values. You know, we truly have some 0 values out here as well. Okay. And so now what I ask for here is the same exact thing. And so now what's the density right there in these particular places? And that's about it. I'm just about done here. And so the last thing I'm going to ask for, and it looks like it's not opening. And so create an interpolated surface of any pollutant. So when you go to this site right here, I'll just kind of give a quick hint here. But when you go to this site right here, in theory, it has a pollutant that you can download for a year and for a state, and it gives you data that you can download. I'll give you a quick look if I can find it in my downloads right here. And if this thing doesn't come back in the next day, I'm trying to look to see if I've got. Uh, I don't see it. Oh, let me try downloads. Okay, all right. I'll make sure I kind of remember that. But a lot of times what we're looking at here is when we look at PM values, you're going to download it as something like this. And this is PM 2.5. If this isn't going to be, if you can't download it by probably later this week, this is what a download from this site looks like. And so you can see all these stations. On the left, it's got a date, the source, the daily measure right here. So for that particular date, it's micrograms per meter cubed. And so this is the measure. This is all the stuff attached to it here. But this has got a latitude and a longitude right here. And so one of the things that I was suggesting is when we download all this stuff, we have different latitudes and longitudes. The one thing that I mainly want to do is I want to create different stations from this data. And so if we go down all the way down to the bottom, we're looking at about 6,000 readings across about 20 to 25 different stations. And while I'm sitting here, I'm going to click Save As and Browse. And this is and to be honest with you, this is where you earn your big bucks. AQS. How do we turn something like this into GIS data? Any ideas? I got a Latin along. All right. Now, what's the problem with this here? The big problem is here, I got 6,000 points here. If I were to just do add XY data, I got 6,000 points, and I got this points over on top of each other so many times. Do you want to look the same point on top of each other so many times? No. So what do I do? What do I do? What do I do? Now, a couple ideas, and the way that I created those data is I ran something called the summarize. What does summarize do? Counts the number of times something appears. And you know what I did? I ran a summary on the latitude because guess what? How many times is this 35.6062 going to appear? Do you think there's any other stations in the entire state that have this same exact latitude? No. So I run a summary on this. While I'm there, guess what I'm going to do? I'm going to average up the longitude for all the same latitudes. And while I'm there, I'm going to go over here and average up all the daily measure values. And so for each station, what am I going to get? You want me to just do it in here? I'm so excited about this. What? You know what I'm talking about? Does anyone else know what I'm talking about here? Now I'm going to show you some of the magic that we can do because I've got this big, nasty 6,000 record AQS data. Think about how much work. I get excited about this because you think about how much work went into collecting this. I'm going to have like 3 clicks of the button and I'm going to be creating interpolated surfaces out of this. Just like that. And those are the things that really kind of that are impressive. And so under homework number 8, like I said before, I'd strongly suggest you downloading your own data right here. But since we're here and I didn't magically delete it yet, so I'm going to go and add the data sitting on my Timothy Mulrooney documents. State modified. And so this is the EPA stuff sitting right here, ready to go. You can see this is a standalone table. This is sitting here as a standalone table. And record this and go back and revisit this if you want to later here. One of the things that I do, it's got a site ID. So you notice these site IDs are all going to be the same. So we can run a summary on the site ID. We have the daily mean. It's got the units, AQI value. And I assume that AQI value is the air quality index value. And so those of you who are maybe a little more tuned to environmental science or whatever, I'm not as attuned to that. I'm just the data guy. I'm not sure what this AQI value means, but maybe you can make associations between AQI and this PM value. Maybe combine it with temperature. And then these are the daily collections on a daily basis. And so it looks like, to be honest with you, instead of running the summary on the latitude or the longitude, I'm going to run it on this site ID. Okay, so I'm going to run it on this site ID right here. And it looks like these site IDs are going to be consistent. So summary counts the number of times something occurs. So I'm going to right mouse click. Oh, doesn't let me kick. Why didn't it let me kick summarize? Oh. I got excited for a second. Doesn't let me click summarize because it's a number and it wants to treat it as a number. Right mouse click, it doesn't let me do that. So real quickly, I'm going to export this thing out. Export table. I'm going to have this done in about 5 minutes here. And I'm just kind of giving you some ideas here. So I exported this table out now to it's not a CSV file anymore. And now, since it's in ArcGIS Pro, now it magically lets me summarize. Okay, everyone see what I did? I brought it into the database. And so now I can run a summarize. And what am I going to do? I'm going to summarize it on what? Site ID. Okay. The first. Now what else am I going to do? Latitude. I'm going to take the average. Longitude. I'm going to take the mean. What's that other thing here that I have? Concentration. It's called 5 concentration. Concentration. That's the actual value. Mean, and just for the heck of it, I'm going to take the AQI value. Now, watch this. I think I'm really smart, but let's see. So when I run the statistics on this thing, what do I get? I get 23 values. What do I got? I got this first site ID. This is going to be consistent. I got a lat, a long, an average concentration, and a daily air quality value. Can you make a map out of this? I can. So my X is going to be my longitude. My mean is going to be my latitude. Look what I got here. Look what I did. Look at these attributes I've got here. This is like air quality data as of like last week, whenever I downloaded this stuff here. And I got 23 stations right here that I can now create an interpolated surface. I can go to my symbology. Let me look at my symbology. Let me look at my graduated symbols under this F5 concentration or whatever. There it is. Look at my air quality right there in the last year. Not air quality. This particularly is my PM value. Look at my air quality indexes. There it is right there. So now look what we have here. You know, kind of aligns with our other patterns that we had before. You can see we've lost a couple of stations right there. Okay, so we ran a little bit of our statistics, or we ran our summarize while we're there, because it doesn't matter if we average up the latitude for the same location. What's the average of the same latitude? It's the number itself. It's the same thing. And then I go to the next latitude, because I bet you if we were to count the number of unique things, it's 23. What are the chances that any two stations have the same exact latitude? No. What are the chances that any of these things have the same exact longitude? No. Okay, because in theory, what are they? They're spatially distributed across space, especially across 4-digit precision. And so we can make a nice map out of that. So by the end of the week, I'll provide an explanation of the data if you can't download it. Otherwise, I'd say, hey, go get ozone, go get PM, go get whatever. I just hear about PM 2.5 because we're an environmental science department and I pretend to be an environmental science person. Okay. And so that's about it for today. This is a really nice exercise. Those of you looking at relationships, environmental health, indicators, all these other things, we can start to look at air quality. You can create interpolated surfaces with this thing that we just did in part 1 and part 2 for like air quality as of this week. You know, so to me, this is really encouraging. These are some of the things that you can do with Thomas. Thomas works for the EPA, Environmental Protection Agency, where we're downloading these data from. Now he's doing, if you heard him speaking, he's doing water quality, water mapping, surface hydrology, and he's doing something as part of EnviroAtlas. So the environmental atlas that the EPA uses for environmental indicators and all that other good stuff. So I'll stop talking here. We got a couple of things to tidy up here with the exercises, but I'm kind of giving you a little bit more flexibility. And as you can tell, I get really excited about kind of you being all the possible questions that you can answer. You PhD students, you can take off in these directions with things like large scale environmental health, asthma, all those other things, as well as position paper stuff where that, hey, you know what you want to do? You go run interpolation routines on these, find the differences between the surfaces, and your position paper is this homework right here. Change the parameters, look at how they're different. So I'm done talking here because my wife needs me to stop at Trader Joe's on the way home. So, all right, I'll see you all later. Have a great day.
Really quick for this, so
Yes.
if I wanted to do my paper on this, for like if I like particulate matter, how many decimal places should I use it like when explaining on a map? Like, should I use
I'd go to 2. I'd
Okay.
probably go to 2 here. You know, but when we download the data, we want to keep as many decimal places as possible. But I'd go
Okay.
to 2 because if you're talking about the average, like the average was 6.37. You know, I think that would be more than fine with me. Or you could put them in a small table like mean, median, mode, range. And so you can put a little table right there that has those descriptive statistics right there, and maybe you can list those out a little bit longer. But in a paragraph, like using embedded within verbiage, I would not go more than 2.
Okay, thank you.
All right.
Was the position paper, like you,